So let's look again at expected values. And I want to point out something different about expected values. So we did the expected value for rolling a pair of dice. And the nice thing about the expected value when you calculated the x times p of x is that and it totaled up and divided by 36, you got exactly 7. So the average roll from a pair of dice was 7, which is nice because you can roll a 7. In fact, you roll a 7 more often than you're going to roll anything else. But there's other games of chance too when you're playing in a certain city in the desert Southwest. For instance, roulette. Now let's imagine betting $1 at the roulette table. If you bet $1 that the next spin of the wheel is going to come up even, there's a 20 out of 38 chance that you're going to lose. That means there's an 18 out of 38 chance that you're going to win $1. So those are the two possibilities. Either you're going to lose $1 or win $1, etc. Well, let's calculate the expected value when you play this game. So x times p of x is negative 20 over 38. 1 times p of x is 18 over 38, which gives you a total of negative 2 over 38. So on a dollar bet, that's about, a little bit over a nickel, about 5.3 cents. But notice something. It's a negative number. All right, we'll take a look back at that in a second. If you did the same thing for the game of craps, this time say you're betting $5, then let me just put in some numerical values, negative 2.54 here and negative 2 or positive 2.46 for a difference of 8 cents. So about 0.08. Now keep in mind that's for a $5 bet. If I put this in a $5 bet, that'd be negative 25 cents. Or maybe 26 cents, depending on these extra digits. Actually, I think it would be 26 cents. So let's just put that there, 26 cents. First things first, why are these numbers negative? What do you think that negative value reflects? Keep in mind what we're calculating. We're calculating the expected value. What happens on average? Yeah, more opportunities to lose and win. On average, you're going to lose money. That's how Vegas can pay for their big light signs and all the big comps and all the other special things you have. When you go in, on average, you're going to lose money, especially if you stay there for a long time. So you have to be clever about it. Which one of these games would you rather play? Would you rather play roulette? You bet $5 on average, you're going to lose a quarter, or play dice. On average, you're going to lose 8 cents. Dice. Your expected value is closer to 0. So it's not as steeply stacked against you as roulette. Roulette has a bigger, what's called VIG, a bigger chance for the house to win than you have. Let's see. Let me just copied something here. Thank you. Where did it go? Where did my sheet go? Yeah, you're right. Um, 251, 290s. Probably a 4. I'll have to double check on that. But the numbers are approximately right. And the point that I'm trying to get across is that there's two things. One is that the big one is that the expected value is negative. On average, you're going to lose money. The other one is that if you're going to play these games of chance, try and find one where the expected value is closer to 0. I mean, there's a huge difference in terms of craps as opposed to roulette. There's a lot bigger chance for the house to win here as opposed to here. So just make some smart bets if you're going to bet at all. But realize that the longer you stay there, the less your chance of winning is going to be. So a decent strategy is to try and make your money and then put it in your pocket and leave. Because if you stay there long enough, the house is going to get their money back. Okay, let's do a couple more with our Google Sheets here. So we calculated mean and standard deviation. Let me help you input the values for problems number 18 and 20. I'm going to show you a little trick that we're going to understand a little bit better after we do section 5.2, and that is where these probabilities come from. But right now, I want to work with this probability table right here. So you have one of two choices. You could either work with it by hand, or we could type it into Google Sheets. So I'm going to opt for Google Sheets. And to do that, I'm going to kind of cheat a little bit. I don't feel like actually typing those in by hand. So let me delete all these values real quick so that I can show you how they're calculated. Start by typing in the numbers 0 through 8. These are the number of girls amongst 8 children that a couple might get in 8 visits to the hospital. So there's your X, number of kids. Here's P of X. So let's type that in here, P of X. And like I said, you could copy these directly from the book. There's nothing wrong with that. In this case, there happens to be a little bit of a shortcut that we can do to copy these or to paste these into our sheets. So would it disturb you if I show you a command that you're going to need in section 5.2 anyways? You're okay with that? This is just a trick to avoid having to enter all these things manually. So follow along. Type in equals binom, and by the time you get to the O, it should fill out the rest of this binomial distribution. And it's just going to give us the probabilities of these things. So we want to type in is binomial distribution, the number of successes, that is the number of girls, that's in column A. So click that, comma. How many kids are there? Well, there's 8, so type in an 8, comma. And then type in a P of 0.5, that's the probability of a girl, is 0.5. And then this cumulative stuff, I'll have to explain that at a different time. Just type in false. So one more look at that probability. And if you compare this to what we have in the book, we're just getting a more accurate version of what they have in the book. What they have in the book just happens to be a little bit rounded because the author didn't want to go past the third digit. And that's fine. Once you have the first one, copy that and paste it down to the rest of them. Now a little bit of a review here. How can I tell if this is actually a distribution? What would I have to check? Yeah, that it sums up to 1. So let's do that. So equals sum, equals sum. And then let's click all these. And perfect, it sums exactly to 1, which is good. Charbel? This calculation. So one more time, what you want to do is you want to type in binomial distribution. So just start typing in equals and then binomial. And after the 4th letter, it should fill it out for you. You want A, which is the number of successes, so in this case 0, comma, 8, which is the total number of people in this experiment, comma, 0.5, comma, false. And then copy that formula all the rest of the way down. I'll explain that a little bit later, or maybe even in the next section. But for right now, all I wanted was just an easy way to get in these probabilities rather than copy them directly from the book. So you don't have to worry about the intricacies of the formula just yet. We'll get to more of that later on. We're going to use this table for two different problems, and then probably some more that I'll kind of make up as we go. Problems number 18 and problems number 20 refer back to this table. So if you look at problem number 18, it's going to refer to this table. And you can work with this table directly. In fact, let's compare things. We want to find the probability that you get exactly 7 girls. So problem number 18a asks for that probability. What's the probability of exactly 7 girls? Now, according to this, that probability is 0.031. All right, great. What is it according to Google Sheets? Get a little bit more precision, right? 0.03125. So number 18a, probability that x equals 7 is 0.03125. Hopefully no disagreement on that one. Let's look at the probability in part B. Find the probability of getting 7 or more girls. Okay, well, probability of 7 or more. What's that probability going to be? Or how am I going to find that? What do I have to include here? Or how is that different than part A? Yeah, because it includes a little bit more, right? Really what that works out to is a probability that x equals 7 or the probability that x equals 8. What's nice about this is that 7 and 8 are mutually exclusive events. So I can calculate this probability just by adding them. Probability that x equals 7 plus the probability that x equals 8. You don't have to have Google Sheets to do this. You've already got the probabilities here. You could do that on a calculator. Nothing wrong with that. Should get about 0.035. If you have it in Google Sheets, though, let's take advantage of that. So let me just do that over here. I'll write it out as probability that x is greater than or equal to 7. Let's see. Probably, there we go. Probably that x is greater than or equal to 7. So it's really equal to this plus this. So you're just getting a little bit more precision with the second method, but both of them work. And what I want you to see in either case is that you're really adding up the probability of both of those events. So I'm not going to copy it down with all the precision. It's about 0.035. We okay with those first two? Thank you, John. Thank you. All right. The last one's a little bit tricky. And so let me help you out with this one. Actually, you know, I think there's a typo in the book. I'm not sure. I'm going to write the author. They say, which probability is more relevant for determining whether 7 is a significantly high number of girls? And I'd have to say 8 births. 10's not been part of this problem. So I'm saying 8 births. The results from part A or the results from part B? Well, I think what's going on is this. The more kids you have, the less likely that any one particular event is going to happen. But when you start looking at probability of at least 7 or at most 1 or stuff like that, then you're looking at probability of this event or something more extreme. And that to me is a more relevant way to determine how unusual your event is to find this total probability. So in the answer to part C, I'd say, yeah, it's the probability that x is greater than or equal to 7 is the more relevant probability that you want to calculate with. Last part here for problem number 18. Is a 7 a significantly high number of births in 8 girls. Why or why not? Well, what was our probabilities here? Probability of at least 7 was 0.035. So was a 0.035 chance going to come through for you very often? No. The author thinks things are statistically or significantly high or significantly low chance if it's less than 5%. So since 0.035 is less than 0.05, that means it's a rather unusual event. In other words, it's significantly high because it's unusual. Let's use this probability distribution to calculate a few more probabilities, and maybe we'll end up with calculating the range rule of thumb, applying that one to this as well. So I promised you I'd make up a couple of my own. Let's find, for example, the probability that x equals 4 or x equals 5 or x equals 6. Find that probability. And also, let's find the probability that x is less than or equal to 2. And the probability that x is greater than 6. So the last one's a little bit tricky. Notice that it's greater than 6. Doesn't include 6. Torturing me. I'm not going to get to these examples again today. Just like a week in my office. Can't get to these things. You'll handle them? Alright, sure. Listen. How many kills? M&M's. So about 28 servings here, 200 calories a serving, so 5,600 calories. Basically, you'd have to run a couple marathons to burn that off. All right, so let's see if we can understand what to do with some of these things. The first one is to calculate the probability that x equals 4 or 5 or 6. Well, with your calculator or with Google, either way is not too bad. Let's go over here to Google. Really what we have to do is we have to add up the probability of all 3 of these events, right? So that's not too bad. So equals sum of 4, 5, and 6. And you got about a 60% chance of getting a 4, a 5, or a 6. Okay, nothing too remarkable there. So let me write that down here on our sheet, 0.601. Now, how about the probability that x is less than or equal to 2? What events satisfy that one? What should I add up? 0, 1, and 2. Good, so this is really probability that x equals 0 plus probability that x equals 1 plus probability that x equals 2. So again, you can add that up. You can add it up by hand if you had to with a calculator. You can do it on sheets. So let's just do it here. Equals sum of 0, 1, and 2. It's about 0.144. Great. How about the last one, though? What's the trick on the last one? The probability that x is greater than 6. What should I be adding up there? 7 and 8. And a couple of you got that, and that's good. The tricky thing that I want you to notice is that really this is a probability that x equals 7 or x equals 8. It does not include 6. 6 is not part of this. So, okay, probably that x equals 7 or 8. Well, we already did that one. That was about 0.035 without getting too precise. But Google Sheets could add that up for you if you wanted to be very, very precise. Are we okay with those 3 examples? Now, a related one would be, what's the probability of at most 5? And I say that's a related one. It's actually related to the one we just did. And to see that, maybe I'll draw out the sample space here for us real quick. All the different things that can happen. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So at most 5. What events could satisfy at most 5? What probabilities do I have to add up? Yeah, 0, 1, 2, 3, 4, or 5. So that's one way to do this. There's another way to do it with the complementation rule. If I wanted to use a complementation rule, what's the complement of at most 5? Yeah, greater than 5. So 1 minus probability that x is greater than 5, or at least 6 would also work. So you could do that one of 2 ways. So here's x is greater than 5, so it'd be 5, 6, or excuse me, 6, 7, and 8. So both of those should work. Let's try that. Let's try it both ways. So let's get rid of all these. Probability of at least or at most 5. Most 5 is going to equal the sum of 0 through 5. Why didn't it work? Equals sum of 0 through 5. Alternatively, I could do equals 1 minus the sum of 6, 7, and 8. And I get the exact same thing. So it works out either way. But one thing I wanted to remind you of in doing this is the complementation rule. Complementation rule can help you out, especially if you're doing this by hand. If you're asked to calculate the probability of at least 7, it'd be certainly much easier to do 1 minus the probability of exactly 8. Let's finish up with calculating the mean and standard deviation of this binomial random variable. Before I do, are we okay with these last few examples? Like I said, we'll finish up with this one here. The mean and standard deviation. Okay, let's get rid of this. Let's remind ourselves on how to calculate the mean from a distribution. So from a distribution, if I want the mean, I want to calculate, first of all, x times p of x. So that'd be equals this column times this one. What do I want to do from here? Yeah, copy those down. Thanks, Nick. Then what? Sum it up, yeah. So the sum. Now, before I hit the enter button, uh, if you have 8 kids, how many do you expect are girls? 4. Half of them, right? All right, let's see that this actually matches our calculation. So if I sum this up, I get exactly 4. Yay. So, it feels like a lot of work to get a result that we kind of already knew in our minds anyways. But we'll talk more about that in the section 5.2. Let's find the standard deviation then. You find the standard deviation. It's going to be P of x times x minus mu. In this case, x minus 4 squared. So find that calculation for this entire column, add it up, and you should get a nice round number for the variance. Make sure you take the square root of the variance to come up with the standard deviation. If you get that done, then try and apply the range rule of thumb to your data set. Try and find mu minus 2 sigma to mu plus 2 sigma. I know that would push you like up front, but there is room up front.
That is a problem because, like I said, if I'm that far up front and I'm clear to see my eyes, it's like a lose.
I know Abby, she's had her shots, and she doesn't bite either way, so it's safe to sit over here. But then that's your choice. But she's had her shots, so it's okay. Okay, so second, let's get out of here. Second list. FYI, second catalog. If you go to the catalog, so like all the managing type, you probably just jump down to S's by typing this. No, it might be better off doing a T. And then scroll up. So shift on the T, and then scroll up. That might be really important. Okay. Now, I'm going to give you a homework assignment that asks ask you to do this kind of stuff, but it's all spelled out. You don't have to have this memorized. Remember, this course is about learning statistics, not learning Google Sheets. Google Sheets is just our means of doing this calculation. You're going to have to do it one way or another, whether it's with a graphing calculator, a statistics package, Excel, Google Sheets. Somehow you have to do this. What's nice about all this technology is that you don't have to do this by hand. I mean, I used to make people calculate mean and standard deviation by hand because that was just, what we had available. But we don't have to do that stuff anymore, which is good. Yeah, I don't miss those days. I'm sure that if you could see a then and now, you wouldn't miss them either. So x times p of x, p of x times x minus 4 squared. Let's do that. P of x is in column B times parentheses x, which is in column A, minus 4 squared. I strongly suggest when you do these types of things that you not click here to get the mu, just actually type in the number. And maybe I can show you why later. But when we total this up, we should get the variance. So equals the sum of all of this, and it should be 4 for the variance. No, 2 for the variance. 2 for the variance. And then the square root of that, square root of 2, is going to be 0.414. That's your standard deviation. To get you apply your range rule of thumb to this now, mu minus 2 sigma to mu plus 2 sigma. Let's do that. Mu minus 2s 2 sigma is going to be equals 4 minus 2 times the standard deviation, and equals 4 plus 2 times standard deviation. So if you had 8 kids, if you're going to the hospital to see what happened when 8 kids were born, what would be the unusual values? What would be unusual to see in terms of the number of girls? Yeah, so the typical values are right here, 2 through 6. So that means the unusual values are going to be at the extremes, 0 or 1, 7 or 8. Those would be unusual events to see those. Okay, are you feeling a little bit better or comfortable with mean and standard deviation range rule of thumb from these spreadsheets? If you have some problems, please come see me, get some help, etc. You're going to get a homework assignment on this. I'm not going to be asking much on an exam for you to do this stuff because I'm not trying to quiz you on Google Sheets. So let me give you some homework. So for section 5.1 out of the 12th edition, so let me go back over to here. 12th edition, try 1 through 19, 25, and 29. If you have the 13th edition, then try 1 through 25. Have a good one. See ya.